The first application example is on mechanical truss design. So what is a truss? Imagine a bridge or imagine an electrical tower. You have seen trusses every day in your life probably. So a truss is a mechanical structure that consists of rigid beams that have been connected together at joints and in some regular grid. And an example of a truss structure is here the bridge on the right hand side, or some Hindenburg type of airship where the hull is constructed as a truss, or electrical towers, the Eiffel Tower and so on. In the last, let's say, 150 years we learned how to construct these towers and also how to compute them, how to trust them. In the first days maybe some of them crash down, today they don't. And that's also due to the fact that we know exactly what the stresses are inside of the trusses, and we can compute what happens to them also if there's wind or some vibrations and so on. And what you see here, these references, these are some of the important improvements that were made during the last 100 years in the computation of the properties of these trusses and also in optimizing their design. So if the truss structure is too heavy, it might break down under its own load, under its own weight. If it's too light, it might not hold the load that we put on top of it. So somehow we need to find a good structure that holds and that is maybe also cheap or economical to construct. In this example we will learn how to exactly do that. But be careful, being able to do the computation does not mean that you're an expert, and does also not mean that you can evaluate the safety risk associated with that. So writing down the optimization problem and solving it is one thing, and it's good to have, for example, then the best structure for your needs. But the domain experts, they do a lot more, and they can not only evaluate the result but also all the assumptions that went into the optimization problem that was solved. So here we learn to optimize, but that does not make us domain experts, just say. So how was this field developed historically? One important figure was Lucian Schmid, and with others in the 1960s he founded the scientific discipline of design synthesis. So to take some description of the requirements and the constraints and then synthesize the best design. And they started with some simple truss structures, for example here this 5-bar tower structure, and then wrote computer programs for their optimization. Initially, of course, the hardware was slow, so they had like IBM 360 series machines and Fortran, and but gradually computers became better and also the methods became better. However, even after the first decade, so in the 70s, this was still considered to be a toy. So the problems they could solve were rather small, like 5-bar tower structures, and no real engineer would touch these methods, also because you still had to be a programmer in order to use the tools. However, in the 80s, when computers became fast enough and the interesting problems could be solved, companies were founded and the tools were developed to be nicer to use, to have graphical user interfaces and to be integrated with computer-aided design tools. And soon these methods that were evolved from some research department became a workhorse and became really indispensable for the engineers in the field. And today many of the structures that are created could not have been thought of without the help of a computer. And today we have more general tools available as well, so we can also do topology optimization of free-form shapes and any 3D shape that can be imagined and optimize that. But for this example we will still focus on the truss structure. One interesting thing concerning here this 5-bar tower structure, so this was included back in the day in research grants or in applications for a research grant, and there is one story where the caption under this figure was that this is an electrical tower, and they wanted to develop methods to optimize the design of electrical towers and get money from that from the American government, and the grant was rejected. And as this was the 1960s, they changed the caption and said, okay, now they want to optimize the landing gear of a moon lander. Back then, when space shuttles and rockets were developed to land on the moon. And actually it kind of looks as if it could be the landing gear of a moon lander. And the same grant then was accepted. So this goes to show that sometimes you know how to market your work. Okay, so the truss structure we want to optimize is making a couple of simplifying assumptions. So we are concerned with a truss that contains a set of beams that are connected to one another. So here I'm drawing them in green. These are the beams of the truss, and these are connected to each other. And the connection points, these are called the joints. So here we have all the joints, and some of these joints are taking on an external load. So here we have the load, like some weight and gravity pulling to the ground. And in addition, we also have cantilever points, and these are the points where the truss structure is connected to the ground or to the wall or to some fixed point. And our goal is to find a truss structure that is as lightweight as possible, where we assume that the x and y coordinates of all our joints are fixed. So we make the simplifying assumption that this truss structure doesn't move when I am adding a load, and which is reasonable if our truss structure is sufficiently strong. But of course, every truss structure has to move a little bit in order to exert a counterforce when I'm putting load on it, because every force has a counterforce acting on it. But we make this assumption that the joints don't move, and we know the joints ahead of time, and we also assume that the truss itself has negligible weight, so that we don't have to consider the gravity of the truss structure itself. So these are the assumptions we are making. And what we then have to consider are the so-called equilibrium conditions. So there are forces going along in the direction of the beams in plural, and when the beams meet at the joints, the forces that go in the direction of the beams, they have to exactly cancel out. So here we have a force going in the direction of this beam, a force going into the direction of this beam, and a force going in this direction. And these forces have to cancel out so that the sum of these forces in every direction is exactly zero. And well, the forces can be positive or negative, so we can have tension and compression, and still it has to cancel out. And in a real truss structure this is the case. If it weren't the case, the truss structure would be accelerating and moving, and obviously this doesn't happen. Okay, so from the forces going in the direction of a beam, how can we compute its y and x coordinates? So let's say here we have a force going in the direction of the beam, and we want to decompose that. We want to decompose that into a force in the x direction and another force in the y direction. And for this, well, it's clear that we have to use the trigonometric functions of sine and cosine. So the strength of the force here in the x direction, this is exactly, if here we have our angle theta, here we have exactly then cosine of theta times the force of the beam, and the force along the beam, we consider this to be a scalar. And we can write this down in a more simple fashion. So you know maybe from high school how to compute the cosine of theta. So now if theta is down here in this angle, then theta will be the length b, or here the length b, divided by the hypotenuse, so the length c. And if we now call this here our, if we represent this c line here by a vector, and we're calling the vector db, which like the direction of the beam, so here we have db, then we can compute the length of the hypotenuse as the Euclidean norm of dB. Here, Euclidean norm. In order to compute the cosine of theta, here then we take dB in the x direction divided by the length of dB in the Euclidean distance metric. Okay, and so you can see from this how this expression up here, this ends up with a vector, and the vector is then exactly the force along the beam in the x direction and the force along the beam in the y direction, like that. And now Newton's third law comes into place, that the forces between two objects exist in equal magnitude and opposite direction, and have to cancel out. And therefore, if we take then the sum of the forces on the beam, they have to be exactly zero. So here we are still in the 2D domain. So here we have 0 in the x direction and 0 in the y direction when we sum up all the forces. But for that, you also have to consider the external load. So if there's a force acting on one of the joints, we have to add that to the equilibrium condition. Okay. And with this equilibrium condition in place, we can ask ourselves the question, well, what do we then want to optimize? And we want to minimize the weight of the truss so that it still holds a given load. So the weight of a certain beam is defined by its cross-sectional area. So we know the length of the beam because the positions of the joints are fixed. And now when we look at the beam here, it has a cross-sectional area. And then the weight of the beam would be the volume of the beam, which is the length times the cross-sectional area, plus some constant factor that depends on the material, like what type of steel you are using, for example. And we know how much cross-sectional area we need at least for a certain force. So if there's a certain force, so tension or compression, acting along the direction of the beam, we know how thick to make the beam at least so that it can safely hold this force. And then we are minimizing the weight or the cross-sectional area so that it is exactly at what is required. And from the literature, then we have a certain factor, here it's delta, and the mass of the beam is then the length of the beam times the absolute force, so either tension or compression, acting along the beam, times this delta, and this delta then it combines all the knowledge from the literature, what cross-sectional area we need depending on the force, and there is some linear relation between them. Okay, so depending on the forces, we can compute the required mass of each beam. And now the question remains, how much force has to act along every beam so that the entire truss can be in the equilibrium condition that we need. So we are now minimizing over all the forces under the constraints that the equilibrium is always there. And this looks like a normal linear program with some equality constraints, and we know how to solve that. There's just one problem here, and the problem here is this absolute value. So here we have an absolute value, and well, as we have already discussed in one of the exercises, we have a problem with absolute values, because at the 0 point there is no gradient defined. And somehow we need to get around that and still define this in a way that we have a convex optimization problem that we know how to solve. How in general do we deal with absolute values? And there's a certain trick for doing that. So originally we are minimizing over the absolute value of f of x. And now we want to transform that into a convex optimization problem. And what we do is we are adding an additional variable s. And what we want to achieve is that s is exactly the absolute value of f of x. And in order to do so, or in order to achieve that, we have to add two inequality constraints to our optimization problem. In order to understand what happens here, we have to look at two different cases. So we have the first case where f of x is bigger than 0. And now the optimization problem looks as follows. We have here our coordinate system, and since we're minimizing s, it looks exactly like this. And the function that we're optimizing. And now we have added two inequality constraints. Let's say f of x would have this magnitude, and then we require s to be larger than f of x, which would be here, because f of x is positive, as we said. And it has to be larger than minus f of x, meaning this area here, we are excluding it by the inequality constraint. And this area, we are also excluding it by the inequality constraint. And we know then that s will sit exactly here at the place where the constraint begins, because we have a force to minimize s, and this is like pushing the solution into the inequality constraint. And now let's look at the other case. Let's look at, or let's finish this up here. So we know then that s is f of x, or that s star, the optimum here, is equal to f of x. And then for the case 2, we have f of x smaller than 0, and let's just clean this up. Cleaning. Now again we have the coordinate system, we have our function that is just s that we are minimizing, and now we have the first constraint that says s has to be larger than f of x. F of x is something negative, so again we are excluding all of this area, and also s has to be larger than minus f of x, and minus f of x would now end up on this side, and we are excluding this area. And again, s ends up here because we are exerting pressure. We want to minimize s and pushing it into the inequality constraint. And therefore here as well, in the optimum, we have s star, this times minus f of x. And that means, in conclusion, that s star is the absolute value of f of x. And this is exactly what we want to have. But you need to make absolutely sure that the optimizer is adding pressure to s and wants to minimize that. And that becomes important later on when we have several of these variables of which we are taking the absolute value, or when this is hidden somewhere inside an equation. You have to make sure that there's actually an incentive for the optimizer to push our additional value towards the absolute of f of x, if f of x is what we're interested in. Okay, now with this we can state the full optimization problem for computing the minimum weight design of our bridge. And this is a linear problem because delta is fixed, the length of the beams is fixed, and now we just have take the sum over all beams and here look at the absolute value of the beams that we have created by adding these additional constraints. And we see also that there is pressure exerted on the absolute values, so we know that here this upper relation here, this is actually holding. And the side constraint is the equilibrium condition for every joint. So we have optimization variables in 2 times the number of beams, because we have added this f tilde b, and we have equality constraints 2 times the number of joints, because for every joint we look at the equilibrium in the x and in the y direction. Now, what does the design space look like? Now let's take here some example. We have a bridge that shall span a span of 18 meters, and as the design space we have defined a grid of 18 by 7 joints and beams connecting these in a regular way, and we can connect the bridge to the ground at 6 cantilever points that are here marked in red. And the center line, which is blue, this is where we'll have our road, or the rail track where the train is driving. And here we are adding a load, an assumed load of 20 tons or 20,000 kilograms times the gravity constant, acting in the x direction on every joint that is here on the center line. And the question is, how lightweight can we make each of the beams so that the bridge will still hold this load acting on it. Now compute. We are optimizing linear problems. We can solve them quite fast with our computers today. And this is the optimum result. So we will have a bridge design that actually resembles many bridges that exist in real life. So this seems to be like a natural solution. And this bridge then has a weight of 3,000 tons. So the weight of the bridge itself will no longer be negligible, and we would have to include that in the optimization itself. But including the weight of the bridge in the optimization itself, this is what you will be doing in the exercises, because this is one of the practical examples that we will solve all together. Just giving you a hint of how to include the weight itself. What we will be doing is we look at the beams and at the joints connecting the beams, and then we make an assumption that is that the weight of the beam will be distributed evenly across the joints. So we will cut here in the middle and say half of the weight will be added as an external load or as an additional load in the x direction on the joints that are connected to this beam. One observation that is also relevant going forward is how do our equality constraints look like? And here again we have a SPI plot for the equality constraints. So again we can combine all the equality constraints in a big matrix equation, ax minus b equals 0. And the matrix A has a very interesting structure because it is very sparse. So most entries of this matrix are 0, and there are approaches to exploit the fact and to get many orders of magnitude improvement in speed when we can ignore all the elements of this matrix that are 0, and later we will see also how to exploit this fact ourselves.